We're going to get started. Today we're going to talk about differential privacy and a bunch of related topics. And here today is a guest from Alan Turing Institute, Ali, who is a postdoc with Adrian, and he's going to start us off. So.
Hello, everyone. Thank you everyone for inviting me here, and it's a great pleasure to see you all here. So today we will be talking about differential privacy, why we need that, and then membership inference attack, and then federated learning that the industry is using to preserve the privacy, to see if really preserving our privacy or not. So why not starting by this question that why should we care about the privacy? If you have any thoughts on this, we appreciate it. That should we care about privacy at all?
Yes, little.
So we know that machine learning models are often rely on the data that we produce in our daily life. For example, in the finance, it can be the transaction or the investing in the stocks, or in the healthcare in cap, it can be the blood samples or heart rate or so on. And this kind of data contains sensitive information about it. For example, they can show our HIV status, they can show our lifestyle, our travel habits, the way that we spend our money, that are our private information. We don't want to reveal this information to others. But on the other hand, we know that machine learning models leak information about their training data. For example, if you consider the service, like machine learning service that provided, for example, by Google or Amazon for the image classification, if you are an adversary and if you just look at the outputs that you get from this API, you can infer that this particular example was included during the training of the model or not. So this is one privacy risk that we consider. And John will be talking about this in more detail later. So now that we know that privacy is important, how we can preserve the privacy. There have been lots of efforts in the past that how we can preserve the privacy, and most of them they were failed. One of them is the anonymization that was failed again and again several times. For example, in the anonymization, what we want to do is that we have a big data set. We want to publish the data set, a version of the data set, but we are concerned about the private information that has in this data. Because this data is contained like the data of the individual. So what we do, we can do some sort of anonymization to make the people sure that, okay, they are secure and they won't be anonymized. But it has been shown that you can be anonymized robustly, like most of the anonymization techniques. For example, in the Netflix example, Netflix at some point created the data set of the people rating to the movies. And then they want to publish this data set for the other researchers for some purposes, like doing some data analysis. For example, in this particular example, training a recommendation system to improve their services or their inference. So the way that they publish the data set is that, for example, they remove the identity information from their data set and just replace each of the users by a specific ID. And they publish this. But later in 2008, we cannot see the reference, but these two persons, they demonstrated that they can break the anonymization of this Netflix data set, which means that they can understand the identity of some of the people in this data set. How they did this, they just look at the word and they say that, okay, IMDb published a data set of their users that they are rating to the movie. And they try to correlate this data set with the Netflix data set that is supposed to be anonymized. By correlating between the rates and the time that people do the rating, they were able to understand the identity of some of the people in this Netflix data set that they were anonymized. And these failures happen again and again lots of time in the literature of the privacy. Basically, one of the main reasons that this happens is that the adversary can look around and find some background information, some side knowledge, and based on that, can break the anonymization. For example, here, if you don't know this IMDb dataset, you cannot de-anonymize this dataset, right? So this is the adversarial side knowledge or background. So now what we want is that we want a privacy protection method that is robust to this kind of adversary knowledge. Even in the worst case, with arbitrary adversary knowledge, we should be able to protect the privacy and define the privacy. That's where differential privacy, which is the gold standard of formulating the privacy guarantees and bonding the information leakage shows up. So basically, the differential privacy says that an algorithm is differentially private if it always effectively produces the same output on the neighboring data sets that differ only on one record. For example, in this example, in the top data set, you see that we have the record of this particular individual in the data set. But in the bottom data set, you see that we don't have the record of this particular individual in the data set. So what differential privacy aiming to you don't understand the presence or absence of each record in the data set. So now let's calibrate our expectation from the DP. What we expect to protect for us DP. Differential privacy or DP says that if you drop a user's data point, is unlikely to change the output. For example, if you do the analysis that smoking caused the cancer, if I'm in the data set or if I'm not, still you get the same information that, for example, smoking caused cancer. So it means that if you look at the output, you cannot tell if a user was in the data set or not. So if you cannot say that, you cannot infer any information about the record of that individual. That's why it's robust against the membership inference attack that we will talk later, and like those kind of data reconstruction attack that they try to reconstruct the input data based on the output. So this is what we expect from the differential privacy. But we don't expect that this prevent the statistic that we want to get from the analysis. For example, if the smoking caused the cancer, we still want that. So this is not privacy violation, just to make clear. Algorithm when you train the machine learning model, but it can be for the data set as well when you want to publish your data set and you want to do the anonymization. Maybe if I first define the differential privacy for more formally, you can have the better understanding of that. So more formally, differential privacy says that the probability that your algorithm M outputting the solution S on the data set D is close to the probability that your algorithm M, the same algorithm, but this time taking the data set D prime, outputting the solution the same solution S, are very close to each other. And they are very close within an interval that is bounded with the epsilon. And here epsilon and delta are the privacy budget in the differential privacy. The smaller the epsilon, which means that these two probabilities are closer, so we have the stronger privacy guarantee. And why we have the delta at the end? Because if we don't have the delta, we will have the, like they call it as a pure differential privacy. But it's very hard to preserve the privacy of all the solutions. Some of the solutions are very, I mean, unlikely to happen. So we tolerate for those. That's why we have a delta here, which should be very small, like 1 divided by the size of the whole data set that you have, for example, in your case. When we have the delta, we have the approximated version of the differential privacy that is mostly used because of this difficulty that I mentioned. So now, if we look at this for the training algorithm, when you want to train the model, the differential privacy tells you that you are looking for a learning algorithm that is when it's trained on the neighboring data set D and D prime, the output of the learning algorithm, which is like, for example, the parameters of your model, are indistinguishable to an adversary. So the adversary cannot understand that these parameters are coming from the training the model on D prime or on the D. And later we will see that how we can make the training of the model, deep neural network, differentially private. Any question here?
Just a question. So when you're saying you have a different record, does that mean you can omit a record, like the leave one out sort of thing, or is it you just perturb the record? Does that definition matter?
Yeah, exactly. So we can consider all the possible scenarios, either removing the record, adding the record, or perturbing the record. So the privacy going to just change by a factor of 2. Yeah. So that.
Just a follow-up question. It would seem that adding a record would be a lot harder thing to protect against, depending on what assumptions you make about possible records that could be added. Like if I added a really extreme record, that could have actually quite a large effect on machine learning. So I'm surprised that it's surprising people put that support. I'm surprised the guarantee any matters like that. So it seems to be much harder than potentially adversarial record.
So yeah, it's harder, but I mean at the end, so we will see later that when you want to make the model DP, you control the sensitivity of the model, which means that you control the effect of each of the data points on the output.
So I think you need a much less great sensitivity if you want to protect against
In terms of the privacy, as long as, for example, you bound the sensitivity of the function to each of the record, for example, by constant value, you should get the same privacy band. But the issue comes from the utility. So now, how much you are losing the utility by doing this kind of restriction on the sensitivity that we will see later.
So I agree with your intuition, but I think the reason why it comes out the same way is that you don't want to make a restriction on what it could have been that was in the database in the first place. Yeah. So it actually might be symmetrical.
I think in practice you stretch out the output. So as you go too far to the extreme.
Yeah.
Yeah, it's just change after that point.
Yeah.
So presumably you could do better on
Yeah, exactly. We will discuss that when we compute the sensitivity.
But when we do this, is it are you considering the average case or is it like the worst case?
Worst case, so differential gives you guarantee in terms of the worst case. That with any arbitrary adversarial knowledge that was breaking the anonymization, so here are like control.
What kind of assumptions are made about the data sets itself in terms of their size? Because my data set he only has one example or two examples, and you remove one. I'm not sure can make strong guarantees that where that still hold.
We're going to talk about that a little later, actually. Yeah, because we did work on doing differential privacy on very small data sets. Usually, delta is set to be 1 over the size of the data set. So if there's 1,000 points, delta would be 10 to minus 3. If there was only 2 data points, delta would be 0.5, so it would be quite large. Okay. And so it's hard to protect small data sets.
Equation still holds, but
guarantee
exactly.
Exactly. Yeah, that's.
Okay. So differential privacy is the definition. So now let's see how we can make an algorithm differentially private. So what is the mechanism to do that?
This piece left with the try that out. Oh, there we go. There we go.
Okay, perfect. So one way to make an algorithm DP is using the Gaussian mechanism. So what it does is that, so you have your algorithm or function f of d. So what you do first, you compute the sensitivity. Here in the Gaussian mechanism, we compute the L2 sensitivity, which means that how much your function changed by modifying one data point in the word space, which is like the sensitivity that you compute using this equation. And then when you have that sensitivity, for each coordinate of the output of your model, for example, if it's k-dimensional, you draw the Gaussian noise with this standard deviation, which is proportional to the sensitivity, the desired privacy budget that you want, epsilon and delta. So now you have this, that there is a proof for this, that when you add this noise to each of the coordinates of your function, your algorithm now is differentially private. And I think we discussed this before based on the question that you asked. So the noise that we add, it depends on the sensitivity. One of the things that depends is sensitivity. So more sensitive function needs to add more noise. So it's harder to privatize the more sensitive function. And it depends on the privacy budget that you want. So if you want the stronger privacy budget, you need to have the like a smaller epsilon under it. But it means that you need to add more noise.
One question on this. So on the last slide, this F is the output of the neural network or the output of the learning algorithm, because these means two different things. That means the learning algorithm will output the weights of or parameters of the model that are learned, while it can also be the output of the function that I'm learning. Well, which precisely in this case do we provide a restriction?
So when you want to make the algorithm or a function differentially private, you work on that function. So you compute the sensitivity of that function. For example, here in this example, the function that we want to make differentially private is estimating the mean of a data set. A simple example, right? And let's assume that we have n data points and each of them are binary vectors 0 or 1. So we need to compute this sensitivity. So we look for the worst case scenario. That, for example, if the first data point 1 and the first data point change from being always 1 to being always 0, this will have the maximum effect on the estimation of the mean that we are looking for. So based on this, we build our neighboring data set, which is like all the other data points plus x1 as a d, and d prime is like all the other data points plus this x hat prime.
So just to understand this better, in this case, we are assuming that the attacker only has access to the function outputs, not the parameters, because that would otherwise. Okay. So the threat model is only on the model outputs.
Yeah.
Though I think it is stronger that even full differential privacy, even if there are gradients and parameters in the model, it should still hold.
So before adding noise to the parameters, the adversary shouldn't see that.
Okay.
After you add the noise to the parameter and it's differential private, so I mean, it doesn't matter that what are the knowledge that the adversary has.
Can you apply this post-hoc? So if you didn't train a model to be DP during the training process, can you then take a model and make it?
So it's a very good question. So later we will see that how we can make the model differentially private. But if so, we need to look at each of the steps and make each of the training iteration differentially private. Otherwise, if you just look at the final model, it's hard to see that what is the effect of each data point in the final model. What we can characterize the effect of each data point in each training step and bound that. So we will see in the differential private version of the stochastic gradient.
Let me just quickly comment on that. It depends on training model. So if you train it using SGD, it's really hard to trace through what inference you train those like so you have a method and a method or something like that. Just average. Then it can be possible to say. So, it's easy.
Exactly. Okay, so now we saw that in this toy example, how we can make this function differentially private, right? By adding this noise to the each coordinate of the order. So now let's go to the training of the neural network that we had some question. So typically the way that we train the neural network, for example, using the stochastic gradient descent, what we do at each training iteration, we sample a mini batch of example. We compute the average loss on this mini batch and then compute the average gradient of the loss with respect to the parameters, and then we update the parameters. So now let's see how we can make this differentially private. To make this differentially private, we need to impose this rate changer. The first one is that instead of computing the average loss, we need to compute the per example loss. And instead of computing the average gradient, we need to compute the because we want to see what is the bound on this. So what we do, we artificially clip the L2 norm of each, for example, gradient by C, for example, and then we add the calibrated noise to the aggregated clip gradient. The L2 norm of the gradient by a constant value C, which means that if the L2 norms of your, per example, gradient is above C, the gradient scales down C. But if it's less than C, it will be preserved. And that you have this clip gradient, you aggregate them and you add the noise using the Gaussian mechanism that we just saw based on the sensitivity C and the noise multiplier. This noise multiplier depends on the desired privacy budget that you want to have the differential privacy guarantee, and then at the end you update the parameters using this.
For C, is that like a hyperparameter that you need to tune?
Exactly.
And if so, how sensitive is this to that choice?
It's very sensitive actually, so you need to do like grid search or those kind of advanced hyperparameter tuning to find a good C that gives you a good trade-off between the utility and privacy. Because if C is very small, you are discarding lots of information about your gradient, and if it's too large, you are adding too much noise. So it needs to be, I think John have some experiment.
Yeah. I've never done any base opt on any work before. You know, you usually try 2 or 3 learning rates, and it's all good. This, you need base opt for sure. And you setting the noise and the clipping is really, really hard.
If you're doing a search over numbers the same, does that break any of the DP assumptions?
Exactly.
Because now you know that a C has been chosen such that you get good accuracy.
Exactly. So this hyperparameter tuning leaks some information, but as is just for one singular value, usually people ignore the privacy leakage of this, but there are some papers that show that how you can take into account the privacy leakage of this and then add it up with the epsilon, which is very detailed.
So if the noise is added at a gradient step, is there some notion of like averaging out noise over the course of many gradient steps that you need to take into account when the these DP properties?
You mean that the noise might be cancelled out and you,
Yeah, it's like say that say I took like one big gradient step with a blending rate of 1, right, and I added some amount of noise, but instead I could have taken 10 smaller gradient steps, right? And then if I add IID noise on each of those, then that might be some kind of averaging effect that allows me to recover. I mean, this is just like a vague intuition about adding Gaussian noise times and what happens when you do that, and is that a problem?
right? So the way that we do here is like at each iteration, for each of the gradient, we draw the independent noise from the distribution.
Like it seems like if I'm not doing enough gradient evaluations, I can at least recover kind of the average gradient across my subjects. Which would be the same as one.
Averages, but okay. What is which stage ones?
So maybe the question is there a term in this that is the number of gradient evaluation steps?
Yeah.
Yes.
And I think maybe that.
Yeah.
The more iterations that you do, or more gradient steps that you do, there's the more noise.
Okay.
So that comes into your budget. And back to the hyperparameter tuning, not only do you have to tune the clipping and the amount of noise, but how many epochs or iterations you could do in your training.
Okay. Well, yeah,
And so it's a magic combination of all of these things, which makes it quite true. Basically, learning under this regime is hard.
And like, because at each iteration, I mean, you're touching the data set again, right? So you consume privacy at each iteration, but there are some composition, like advanced composition, that try to have like tight privacy guarantee that, for example, if you train for n iteration, instead of having like n epsilon privacy guarantee, if each iteration is epsilon, how can you make this tighter by having the square root of it?
Yeah,
So the learning algorithm has to be really efficient in terms of extracting information, because you can't just take 10 times as many steps.
yes.
Yeah,
That'll really-
exactly.
Exactly. And the other thing that's not in the slides is both TensorFlow and PyTorch have accountants that keep track of this work. And so you can use their optimizer that keeps track of the noise. And so you can say, I want this privacy budget or this value of epsilon, and it'll kind of help you figure out what you need to do to meet that budget.
We will discuss this kind of limitation of the this DPSCD for the learning algorithm that needs to be efficient, converge fast.
So in relation to this, a few questions. To my understanding, DPSCD is built in such a way that every step has, if you regard as like one gradient step as your F, right? Then there is a specific, epsilon delta guarantee on every single step.
Yeah.
And then you compose them together.
Yeah.
So that then the aggregate epsilon and delta are some value which is
Yeah.
larger than each individual step. My question is, what is the rule for composing these? Like if I have a gradient step that is epsilon delta dp, then I do L of them. What is the rule for keeping the aggregate epsilon delta?
Yeah. So the simple composition property of the DP says that you just need to sum up the epsilon of each of these.
What about the delta?
So the advanced one is, so if you have n times epsilon, so the advanced, there is some advanced composition that says that instead of having n epsilon, you can have the square root of n epsilon.
And what about the epsilon parameter? Is there also a composition for delta or?
I think it's the same for the delta as well.
Yeah.
It's because it's usually done on the pure DP setting, which is like the epsilon, but I assume it should be similar to the delta.
Yeah, on that question, actually, I don't
know the theory as well, but I think, are you working with OFSI and Helsinki? And were you involved in some of that DP work? Yeah. He actually showed me something yesterday of a way to compose the Gaussian mechanisms in a slightly better way that is better than a sum. And it was quite an elaborate relationship, but quite effective. And we're not going to get to that here, but let's just say there is a way to compose that sort of sum is the worst case.
So we're flipping the one of each example, or like the per example gradient, to make this direction of the gradient biased as well. So we will end up with different.
Exactly. This is what we present next. So when you do the gradient clipping, as you said, we are discarding some information, and it will bias the learning algorithm, the path that we take for the gradient descent, because it's in combination with adding a noise. So this is one issue for the DPSGD. So now the path that you take is not aligned with the direction that you, for example, might get in the stochastic gradient. And another issue I think we discussed about the efficiency. So we need to do limited number of the iteration in the DPSGD, because as we said, in each iteration you are revealing information, you are touching the data set, you have the privacy that you are consuming. So we need a learning algorithm that is efficient and like fast in terms of the convergence. And as we discussed, this hyperparameter tuning, that because we are introducing some new hyperparameters of the clipping value, the amount of the noise that we want to add. So it again has the issue of the hyperparameter tuning. So now let's see that if we just use the learning algorithm that works best in the non-private setting, can we expect that this works best in the private setting as well? For example, in the classification case, we are mostly, working on the cross-entropy loss function, and we optimize that, for example, using the SG. But we show that when you optimize the cross-entropy with the DPSGD, it caused exploding the logit values, which is like the output of the model before applying the softmax, and the weights, the model weights. And then when these two explode, they contribute to the gradient computation. So the gradient explodes as well. So when the gradient explodes and becomes large, when you clip, you discard more information. So when it makes it difficult to control the sensitivity of your function or algorithm. It, have a reasonable effect on the utility, which is the correctness of the gradient and the path. And then another issue is that cross-entropy is not noise tolerant, so we add the noise. So it's better to have a loss function that, for example, has a smooth local minima, that when you change the parameter, you don't increase the loss by too much, as opposed to sharp local minima. And the training convergence is not that fast for the cross-entropy. But unfortunately, like all the existing implementation of the DP and DPSGD using the cross-entropy. So now the question that we ask is that, can we design a loss function to alleviate this kind of issue and tailor it to the specifics of the DPSGD? So, therefore, we do this by having the loss function including 3 terms: sum square error, focal loss, and the regularization penalty that I will discuss each of them, with the goal of having the faster convergence, limiting the information loss from the norm clipping, and being tolerant to the noise. Because we want to improve the trade-off between the privacy and utility. So the sum square error is defined on the logit values of, for example, HIM is the logit value of the example I, and it's in the last layer, which is layer M. and the yi is the ground truth level of that example. And the focal loss modifies the cross entropy loss such that it reduces the loss of the easy and well classified example by this factor. And this factor, the higher it is, it reduces more the effect of the easy and well classified example. And when we plot the privacy budget epsilon as the x-axis and the test accuracy that we get at the y-axis, we see that at the beginning of the training, sum square error converges faster than the cross entropy, which is the black, the orange and the black. So the sum square error, which is orange, is converges faster in the get the better accuracy at the beginning. Sorry, cross entropy is the red one, and the focal loss is the black one. And then at the end of the training, towards the end, the focal loss works better because it focuses on the difficult example based on this weighting. So what we do, we impose a structure of curriculum learning that at the beginning, we let the network to be trained using the sum square error, and at the end, we shift the focus towards the focal loss. And then if we look at now to the logit values and the weights, we see that the new loss function that we just designed, it somehow controls the exploding of the logit value and the weights. And we can see the effect of that when we plot the histogram of the L2 norm of the, per example, gradient. We see that the new loss, which is like the green, has much smaller L2 norms of the, per example, gradient. So we discard less information when we do the clipping here. It's like naturally smaller. And to see the effect of this preconditioning of the gradient to the clipping, we compute the divergence between the aggregated clipped gradient and unclipped gradient to see that how much we are diverged from the gradient path. And here we are using the cosine similarity. We see that our gradient path is more aligned to the unbiased unclipped gradient.
Just wondering, this clipping thing, you always use a constant magnitude at which to flip, or could you make that clipping parameter a function of your gradients to say, like the mean standard deviations of the norm of my gradients, and then you just scale your noise appropriately, and then you serve privacy, but you can kind of deal a little bit with these exploding gradients. Is that something people do?
Yeah, I mean, so the state-of-the-art method, they use it constantly because it will increase the complexity of tuning the hyperparameter. And it has been shown that even if you use the dynamic clipping, it doesn't help much the trade-off between the accuracy and privacy. Okay, and now we see that when we have all of these terms together, you see that we can improve the accuracy, the trade-off between the privacy and accuracy. Oh, sorry. For example, the red one is like using the cross entropy, and the green one is using the R design loss function that can, in this benchmark data set, cipher and pattern and misalignments. This is one way to address the issue of the DPSGD. And now John will be talking about how, if we have public data set and pre-trained model, can improve this trade-off.
Thanks. Thanks. Okay. All right. Now, in the last year or so, Ali showed some graphs of training models from scratch with DPSGD, but the best models so far and all the recent papers have started from some massive pre-trained model on public data. So in theory, privacy doesn't affect those, although there's some issues, and then sort of fine tune it on public, or sorry, private downstream data. So there we go. This is just a chart full of numbers that I'll explain from a recent Google paper. So if you, these top two bars here are trained from scratch. So here's CFAR 10. And similar actually to the graph that Ali showed earlier, if you want a fairly strict privacy budget at epsilon 1, you get 56% accuracy. And if you want to loosen that budget, it goes up. And so that's training from scratch. Similarly, if you have a bigger data set like ImageNet, they don't even try to get epsilon 1 training from scratch. It's just too hard. And even with a fairly loose privacy budget of epsilon 8, there's only 32%. But down here, they start from some pre-trained massive model. So if you take CFAR 10 and use a model pre-trained on ImageNet, wow, all of a sudden your numbers go up in the 90s, almost independent of epsilon, because you know, the pre-trained model may not have seen CFAR before, but it has seen data like it, and you can just do a small number of fine-tuning steps, you know, use a very small noise budget, and get good epsilon values. Similarly, with CFAR 100 trained on ImageNet, you can get pretty good numbers privately, assuming you're starting from this big model. Now, one of the big feats is here is this JFT model is Google's in-house 4 billion image trained thing. And they can get in the 80s% accuracy on ImageNet, which is close to even non-private numbers, which I think are just touching 90% now, by pre-training on this massive thing and then fine-tuning on ImageNet itself. And similarly for this places data set, that's a little more challenging. So the message here is starting from pre-trained models, you can get much better numbers. Yes,
I think here we still need privacy everything here. If you just take the pre-trained model, apply some fine-tuning. If you don't change your model that much, maybe you don't lose much privacy on your fine-tuning data set anyway.
Well, that's what's happening here. And yes, with a certain privacy budget, you can get better accuracy because you're not changing your parameters very much.
If we don't do any differential private training.
Oh, well, actually, we're going to get there. If you don't do any privacy training, it turns out the models are quite vulnerable, even in the pre-trained case. And that's coming in a slide or two. Yes, Rich.
Generally, much of privacy work, the real trick to getting this getting some synthetic or real non-private data to extract the training of. The chat users won't use private data for most of them. So you might be simulated to get that data.
Yeah. And there is some downsides with just the slide of it. This is, again, I won't spend too much time, but this is fine-tuning large language models. BERT model on the left side that does sentence classification, and a GPT-2 model that's doing text generation. And the dashed lines at the top are kind of the non-private numbers. And these are two different algorithms done with differential privacy of epsilon 3 that you know, don't quite hit non-private, but are getting close. And there's a note here at the bottom is sometimes it's nice to know what a record means in terms of differential privacy. I mean, when Ali spoke, he said if you remove one record, and you know, in sentence classification, a record is a sentence and a label. But in natural language generation, a record could be much larger. It's a whole dialogue history, and so you can have record level privacy, and we're going to see down the road when we do federated learning, there's kind of full user level input privacy, which is even stricter. But both wherever there's foundation models, natural language images, starting from that, you can get decent utility and still get privacy. Okay, But there's some issues. There was a paper just in the last couple of months written by some folks that are big in the community of privacy, and they're basically saying, well, yeah, you're pre-training off all that public data straight from the web, but maybe it's not all that private. Maybe there's sources there that people really didn't want trained into your model, and this is even coming up in the news where the some of the generative images models are being sued by images copyrighted that they're trained on, because they're just scraping things from the web, and they're taking news images that you're supposed to pay a fee for, and they're putting it in the model. So not only that you might be using proprietary data in these public models, but inadvertently there could be lots of other sensitive data just scraped from the web. And so it's becoming an issue legally, and even so. Are these foundation models, can you assume, even though they're scraped from the internet, are they actually private? So that's one issue. The other thing that happens is all these benchmarks, including the ones I showed in the last couple of slides, where it gets great numbers on ImageNet and CIFAR-10, a lot of those results are where the pre-training data distribution is pretty similar to the downstream fine-tuning distribution. So you're getting a lot out of this public foundation model, and you're really not having to do much. But as soon as the distributions start to change, actually we'll see in a slide that these get quite a bit worse. The other thing that they're arguing is these foundation models are so massive, it's hard to run efficiently on an edge device like your phone or something like that. And so if you can't run it on your phone and keep private data maybe locally, now you have to trust models that are in the cloud, which may have other security issues and having people having access to that model, or maybe the server is compromised or malicious in some way. So basically, this paper had not one equation in it, but it sort of was arguing that, using large publicly trained foundation models and then calling it private may be not the smartest thing. For some reason, when you hit this slide thing, it just takes a while to change. Okay, this is something that we did recently in this group with myself and Sasha and some folks from Helsinki and Rich. And we did the same similar data sets to what were in the previous slides, but we had two things change: the amount of data that you got to train on, and also sort of the difficulty of the data, or how much overlap there was with the pre-training data set. So these models were pre-trained on ImageNet 21K. And when you have lots of data, like 500 examples per class, actually the accuracy gets quite high, even with a fairly strict privacy budget, as the Google numbers showed. But as soon as you start decreasing the amount of that data, you really do suffer. So few shot learning is just really, really hard to do in the private setting. And then this CIFAR-10 overlaps distribution-wise. The exact examples are not in ImageNet 21K, but the distribution is very, very high overlap. CIFAR-100, there's a little less overlap, but again, you still suffer, and you suffer more with lower shots, and you just can't get quite as much accuracy, even with a lot of shots, just because it's sort of a harder problem to adapt to. And then if you look at the Street View set on the far right here, which actually overlaps very little because it's sort of street number things that aren't in ImageNet 21K. Again, your accuracy really, really suffers. And just as a reference, the purple line is non-private, so that's what you could get without differential privacy. And so even on SVHN, it's quite easy to get reasonable numbers, but it's really, really hard to get good private numbers, A, if you don't have much data, or B, if your downstream distribution differs from what you've pre-trained on.
When you say that CIFAR 100 has less overlap than CIFAR 10, what exactly do you mean by that? Are you referring to like the actual classes, or are you talking about like the distribution of the pixels in the different data sets?
Yeah, the distribution over pixels. We kind of have an empirical metric that folks in rich groups that it turns out there was another paper that did something similar. And basically, if you train on all the parameters and you get an accuracy, you know, with all the parameters being free in the model, or you just train just the final layer, if those things are close, it implies that your pre-trained model is good and that the overlap is high. So we, you know, in order to say that it's high, low, or medium overlap, we just say, look, if you trained all the parameters in the network and you got a number and you train just the final layer, how different are those things? And that's not exactly a distribution, but it's a proxy for that. Yes.
So the number of plots that you mentioned out here, are they per class?
Per class. Okay, so now we're going to move on to these membership inference attacks. So I'll get into why you might want to do this, but basically the question is was this network trained on this example? And what could you use that for? Well, you could audit your system. I mean, you could train this with differential privacy, and you want to be sure that it's sort of living up to the dp epsilon delta relationship. And so that's one way. If you're kind of a bad person, you might want to use this for extracting training data set. It's a first step in actually extracting data from a model. And the other is maybe there's a legal question, was this trained on that? And this is coming up a lot on the right to be forgotten, where you, if you want to actually test whether Google actually removed your data point from its training, you could do a membership inference on their model and figure that out. So how do we do this? There's lots of types of attacks, but we're going to assume that we just have black box access, so we only have access to the outputs of the model. The attacker has, or the adversary has, access to the data distribution that was trained on, and it also has access to the training algorithm itself. And there's a little game that proceeds here, and it's so you've got a challenger C, or the person that owns the model, and an adversary A, who is sort of the attacker. And so the challenger basically samples a data set D from the distribution D and trains some model on that. And then the challenger flips a coin, and if it's say tails, or B equals 0, it sets a bit, it samples a fresh point from the data distribution D that's not in the training set little d that it trained the model on. And if it's heads, or B equals 1, it selects a point from the training set. So it's basically saying, I've trained a model, and I'm going to pick a point either that I've been trained on, or one from the data distribution that I have not trained on. And then I'm going to send that to the adversary, and I'm going to ask the adversary to try and figure out, was this point a fresh point, that wasn't trained on, or was it one of the points that was trained on? So there's all kinds of attacks that come out of this game. There's all sorts of little variants, but the one that I'm going to talk about is this likelihood ratio attack. And it's quite clever. And so we take A is the probability that this network was trained on this example cat, and B is the probability that it was not trained on the cat. And of course, if we know that the probability of A is greater than the probability of B, no, then likely this cat example was in the training data set. So, but this is sort of hard. Because A, you could look at as, was this network, given the whole distribution of models that was trained on CAT. It's hard to know whether this network is, or evaluating the probability that it's that network given all the networks that could have been trained on that one example. That's sort of hard to do. But everyone uses a loss as a proxy in this, in the sense that that if the loss of the network on a specific training example is high or low, it gives you some example of the quality, whether it's likely part of the set or not. So basically, the loss measures how wrong the model is. So if the loss is low, it's likely part of the data set, but not surely. And if the loss is higher, it's likely not in the training set, but again, it's sort of not a binary thing. And so what is done here is we use as a proxy, A is the probability of the loss on a specific example, given the distribution of losses of a whole bunch of networks on this specific example. And so we can do this by training a lot of models, some with the example in and some with the example out. And this is where a lot of compute budget gets used up. We've got some data set here, and we randomly take half the data set and we train a model. And then we take another 50% of the data set and we train another model. And we do this a lot, maybe several hundred times, or maybe even thousands of times. And so we have thousands of models, and some with a particular example in it and some not. And so we continue and wait. Okay, so we have a whole bunch of models here now. And what we do is we sort the models based on the ones on the left were trained on this specific example, and the ones on the right were not trained on that example. And we keep track of all this, and we can measure the loss from the ones that it was trained on. So this is a distribution of the losses when the cat is in the data set, and this is the distribution of losses when the cat is not in the data set. And in the ideal world, these things don't overlap very much. Sorry, these slides are kind of slow coming in here. So ideally, what we do is we have a distribution of losses when it's in and a distribution of losses when it's out. And here it's quite clear. You could kind of set a threshold at the loss, and it would be quite easy to tell them apart. But actually, in the paper, they do a little trick. It turns out the loss distribution isn't actually Gaussian, and so they sort of Gaussianize the loss. The loss being the L there. They do a little bit of exponential trick to sort of make it more Gaussian. And what they then do is then fit Gaussians to these two distributions, and then do a likelihood ratio test. Like you would then take a test example and you would compute its loss and decide whether it was part of either the in distribution or the out distribution. And if that ratio was positive, then it's likely in the distribution. And so you train a lot of models, get distributions of losses, whether the example is in or out, fit a Gaussian to that, and do a likelihood ratio test on using the Gaussians. And that was some slides from the paper. And it turns out that these examples aren't quite as nice in reality. We did this for a recent paper, and this is non-private, or epsilon is infinity, and the out examples are here in red. And actually, it's quite easy. Many of the examples you can clearly say are probably out of, that they're high losses, and the model likely wasn't trained on that. There's some degree of overlap, but for many of the examples, it's easy to tell whether they were in or out. As you increase the privacy budget, these histograms start overlapping. And notice that at the bottom, the scale is changing in all these diagrams. So, here there was examples with super high losses, but as you start doing private training, and then if you lower the privacy or increase the privacy level or lower epsilon, the histograms overlap even more. And if you say go to epsilon 1, it gets quite hard to tell which examples are in or out. But there is some leakage at these very edges here. You can still extract some information. And so this is what an attacker would use to kind of decide whether something was in or out. And of course, you could look at the histograms, but what is normally plotted is these receiver operating curves. So this plots, since we are doing this experiment, we know whether the example was in or out, so we can make a prediction with this likelihood ratio test, and then actually see if we're right. And we can plot the true positive rate versus the false positive rate, and get curves like this. And so this is sort of non-private, the purple curve at the top, and the blue one at the bottom is a more strict privacy budget. And this diagonal line is sort of the guessing, like, you know, if you're below that, you have no idea. It's a random guess whether the thing is in or out. And what's important here is picking some low false positive rate where you're unlikely to make a mistake, and then look at the true positive rate, because maybe you can't uncover all the records in the data set, but if you can even get at a few with high confidence, that could be bad. And so you say take a false positive rate of 1 in 1,000, which is saying, look, you know, if I look at 1,000 records, I'm only going to make one mistake, and you know, and 999 of them will be correct. I can take at epsilon in infinity. If I go up and look at that chart, I can get 41% of the examples and be quite certain that they were in the training set. And then as your privacy budget or your privacy level increases, it gets much harder. There's still some leakage, but it's much better. And so basically, sorry, yes.
Sure. I was going to ask, how sensitive is the performance of like integration attacks to using the precise same training algorithm? Like, for example, if we have a model that we're auditing that was trained via SGD,
yes,
and then I do my training, my layer with Adam, how?
Not that sensitive. In the paper, they try different algorithms with different learning rates, and even different pre-training data sets and things. And they show that it's less good if you don't have that information, but you still can do quite well without the exact training algorithm.
And taking that maybe to the extreme, because like, yeah, you mentioned that obviously do such a perform such an attack, you need to train like several hundreds of models.
Yes.
Could you do a like integration like with meta learning? Like, for example, I take my network, and instead of training it with a with standard, you know, SGD type of like training process, I train with meta learning, and then to evaluate these like 100 models, and it's very simple. Just have people looked at that? And
that's actually what we're working on right now at this very moment. Yeah, and so yes, meta learning for attack, or just in general, using meta learning as a privacy mechanism instead of DPSGD. But that's a good point. There could be something there, because especially it would be quite cheap to generate the attack models with meta learning.
But if it's really feasible to run such an audit for like
yeah, it gets very expensive. In this project that I did with Sasha and the folks from Helsinki, we burned an astonishing number of GPU hours. It's just between the hyperparameter tuning and these attacks, it's just I'm sure we caused an environmental catastrophe with this paper. So But, yeah. Hopefully they won't find it. Anyway, so basically, you know, privacy works. It does help shield, and it basically says that unprotected models, it's very easy to understand whether something was what the element of the data set was.
We also use this to get an idea about how good our account is. Because really the likelihood ratio we estimate shouldn't be more than epsilon if it is working. But because when we account, we sort of over account the privacy. You might expect the likelihood ratio to be quite a lot lower.
In many of our cases, it was quite a bit lower, although we found in some cases when at very low values of epsilon, it actually could be quite tight. We have a little thing on the paper, but it turns out that at higher false positive rates or higher weaker privacy levels, higher levels of epsilon, actually it wasn't very tight at all. Like it was not a good actual estimator.
Small comment here, there is a paper that shows that depending on the site knowledge that you give to the adversary from the members of Inference and the more knowledge you give, for example, if you reveal the intermediate result like the parameters, not only the right person, you can get closer and closer to the website and provide the privacy maximum. But there is a gap. But the epsilon is like in the worst case. So you need to increase the knowledge of the adversary.
Okay, so that's likelihood ratio tag, and there's a whole bunch of other tags. This is understood to be one of the stronger ones, but there's a lot of variants. Some require fewer models to be trained, but also some are quite a bit less effective. We've got about 20 minutes, so we'll now move on to federated learning. And the bottom, you know, Tally took some of your ideas from some of the slides that you and Siddharth did a few years ago. So thanks for that. So federated learning, the basic idea is to learn some global model based on data at a lot of distributed clients. And so each client at the bottom here, the circles at the bottom, they have some amount of data, and they could train their own models, but they have a limited amount of data. And somehow they want to take advantage, create a better model based on a whole bunch of clients' data, but they don't want to give up their data. So they don't really want to share data. And so these might be different pharma companies that have private drug data that they're happy to sort of contribute to a better model, but they don't want to give up their data, or maybe it's hospital data that's private in some ways, and so they're reluctant to give up data, but they're happy to kind of have the benefit of a model trained on much more data across many devices. And of course, these things, of course, could be phones, and they're trying to do better word prediction on your typing or something like that. So the idea is you could get a much better text prediction model by looking at many users' data as opposed to just one. So that's the basic idea. And so how does it work? There's a little animation going there, but I'll explain the steps. So all the client models, typically they're the same architecture. It's the same like ResNet or something like that. And they're initialized randomly with either random weights or pre-trained weights. And so every client sort of starts off with the same base. Each client then trains a model on their own data. And they transmit the new parameters to the server. And so that's these in the animation, it's sort of sending the parameters up. And then the idea is that the server aggregates all these different parameter updates from all the clients and does some sort of weighted average of these parameters. And then the server then sends the updated model down to all the clients, And so each client in theory is slightly better off than it was. And this is repeated maybe dozens or hundreds or even thousands of times. So it goes through this iterative training process. And at the end, hopefully there's one very good global model that all the clients would benefit from that. There's also, which the title of that diagram also is then each client in theory could take that global model and fine tune it on their personal data and personalize that model if they wanted. But the idea is, can we get a better model by distributed training? And there we go. So actually, this is, I'm going to go through the same thing, but it's just more precise. So weights the model get initialized for rounds, for each round that I mentioned could be dozens or maybe thousands of rounds. It chooses, actually, usually it doesn't choose all the clients. It chooses some random subset, meaning certain phones may be off, or it can't guarantee, and so it gets a random subset. It for each client, which could happen in parallel, each client does their local training, and the little subroutine for that is they've got a certain amount of data that's split into batches, and they do a certain number of epochs and a certain number of training steps, and then they return that up. And there's sort of a weighted sum of the parameters that are returned. It looks at the number of parameters in each client and weights it by how much data they had. And, say the weighted sum is done. So this is just a more precise version of what was in text on the previous slide. Now, again, this is a screenshot from a paper we did a couple of years ago, and it just sort of shows you the trends. Just look at the blue lines for a moment. This was with a different amount of data on each client. This is CFAR 100, and each client had 10 classes only out of the 100, but it was sort of random which ones they had. And then each client could have either a very small amount of data, 2 examples per class, up to 10. But just look at the blue for a moment. The dashed line at the top is if you trained a model and the server just had all the data, that's what you'd get. The dotted line is what you would get through this federated averaging algorithm that I just described, where after a number of rounds, it's sort of saturated. And so usually the model is not as good as if you had all the data in one spot and just trained it, but it's a reasonable approximation. And this lower bound is sort of just a cheap version that if you trained all the models locally and just did an average of those on one time, you'd get that. So this federated averaging is actually quite good, but not as good as if you had all the data in one place. There's a bunch of frameworks. I'll go quickly. There's one actually out of the computer science department here at Cambridge called Flower that they work on. And so if you ever wanted to implement one of these systems for real, this is a fairly good framework to use. And also the TensorFlow actually turns out to be way further ahead than PyTorch on this. The TensorFlow federated stuff is a very good library for lots of experiments doing this kind of thing. Now, federated averaging, it generally works well. There's actually no convergence guarantees. You can imagine that each client has very diverse data and it's non-IID, and so this whole process is not guaranteed to converge. Communication costs can be quite high. You're bouncing a model back on every iteration, and as models get big, you can be millions of parameters on each round. And so what we've done in some work, and other people have done as well, maybe you start with a pre-trained model and you just fine-tune some subset of that model, the head or certain parameters, and you can only then have to transmit a subset of the parameters, and that can help a lot. But back to the whole thing, the model trained in this way, even though you're not giving up your data, the model itself is still not differentially private, and if someone had that model, they could still extract training data from that if they wanted. So, Ali, you want to take over for a minute? Just gonna go into how you would attack these models, and then we'll look at federated learning, and then that will probably wrap up from there. Sure.
Yeah, I mean, so you might have assumed that federated learning is like privacy preserving because you don't share your data, you just share the parameters of your model. But actually, it's not if you don't trust the server, right? So here, let's assume that, okay, you are uploading the gradient that you're computing locally to the server, right? So what server can do, let's say that it's like honest but curious, right? So they don't do any malicious things, they just curious to see if they can extract something from the object that you send. So here, let's consider a fully connected layer that, for example, the output of this node yi is computed based on the ReLU activation function that is applied on the linear combination of the input x and the parameters y and b, and sorry, w and b. So wi is the first row of the parameters of this layer, which is like all the coming edge to this. So if ReLU is activated, which means that if the input is positive, so it just passed the input to the output, right? So now when you do the backward pass, you compute the gradient of the loss with respect to this set of the parameters, wi. What you get is like the scale version of your input x. And this scale is like the gradient of the loss with respect to the bias in this that you are uploading to the server. Which means that each of these gradients, they have a copy of the input data. So when you do the mini batch training, so each of these gradients will have like a copy of the several examples if it's the ReLU activated for all of those examples. So when you do the easy things in the matplotlib, just you plot the gradient, you will end up with this. So some of them are not clear, the examples, because they are overlaid. Several examples in the mini batch that you do here, just you are adding the gradient of several examples. It means that you are adding several x. So now the question is that, assume that the server is malicious, they can do something malicious. So what they can do to improve the quality of this image reconstruction. So what we did is that if we just force each of these nodes to be activated only for few examples, not for all of the examples, so we will have the better reconstruction at the end, right? So if this node is only activated for one particular example like this, then in the gradient we have the scale version of that only. So we can just easily plot that. So we achieve this by adversarially manipulating the initialization, because this is in the control of the server, right? So you are a user, you either participate in this system or not. You don't have any power to say that how they initialize the parameters or how they structure the network or whatever. So when we have the malicious server, they make sure that the, for example, number of negative values in this row of the parameters is higher than the positive value. So most of the time, the input of the ReLU is negative, except for few examples. And now when we do the reconstruction based on this, we can see that, I mean, in less than 1 second, just using the matplotlib, you can reconstruct the exact input based on the gradient. So there is no privacy here, right? Especially when the server is not trusted and can adversarially manipulate the initialization. So now, John will talk about how we can.
We'll wrap up quickly here.
Yeah.
So we talked about differentially private just standalone centralized models, but what does it mean to be differentially private in federated learning? And the idea here is that you want client level privacy as opposed to example level. So all the data that would be provided in the parameters or the gradients sent to the server, you want all of that as a chunk to be not identifiable to that user. And so that's quite a bit stronger than just example level privacy. But basic idea again is much like federated learning, but we take a batch of clients to sample data from or an update from. The parameter updates from each client now are clipped to some L2 norm value, and then they're sent to the server in a clipped form. They're aggregated on the server, and then the server adds a certain amount of noise. And so, in theory, this aggregated model is now user level, differentially private. Don't worry about this very busy chart, but the message here is it turns out you need a lot of users in order to be private. So down here they have 1 billion users, and they sample on each round 1,000, and they add a certain amount of noise, and actually they can get quite good. These are epsilon values. They can get quite good epsilon values with not very much training. But either you do more training, as we said, and your privacy level gets worse, or if here you also didn't have a lot of users and you had to train for longer to get the same amount of noise on there. Anyway, so there's a trade-off between how long you train, how many of these rounds, and how many users you have. And it turns out that unless you have kind of on the order of 100,000 users, differentially private federated learning is tough. And just to show that, I think this will be the last slide. Again, this is from a recent paper. There's a data set called Flare from the folks at Apple. They have 51,000 users, and there's about 500,000 photos distributed across these users. And it's a 17-way classification problem. And the gray bars are sort of the non-private. If you train this thing without differential privacy, you get these accuracy numbers. And the colored bars are the accuracy you can get with epsilon 2 and the 50,000 users. And the different colors are just different resonance of different sizes and a vision transformer, and whether all the parameters were trained or just the final head layer or the head layer and some adapter level things. And so, but basically the moral of the story here is it's hard to reach the accuracy. And if there was maybe more users, 100,000 or 1 million users, you could get better accuracy at the same privacy level. But actually, one of the messages is actually just training almost just the last layer or the last layer plus these film adapters. You can do nearly as well as training all the parameters, and your communication cost goes way down because you're transmitting many fewer parameters. So basically, federated learning privacy is hard to get to be DP on the final model. But it's also hard in the sense if there are server trust issues, and then you get into a lot of encryption kinds of things as well that we've not even covered here. So federated learning has a bunch of benefits, but it has, there's a bunch of security issues. So I think we'll stop there. And, after 90 minutes, you're probably all stunned and ready for lunch. If there's any final questions, we're happy to take them.
It seems that when you're introducing this noise in gradient terms of this IID,
Yes.
any benefit, correlation to that noise, for measuring, does that cost you some privacy?
know the answer to that. I know there's different mechanisms. I know there's a Potts noise as well as Gaussian noise, and there's different ways. But I'm new enough to the area. I don't know the answer to that question, Ali.
I didn't see any like correlated. So why should it correlate?
Yeah, I'm just wondering whether you could have some correlations in there that would make it converge better and, for instance, like avoid the risk that you're continually turning away in a bad direction.
Yeah, I think that can help in terms of utility, but taking into account the privacy leakage of that correlation.
Yeah.
As long as you can analyze the privacy leakage of that correlation between the nodes, I think you should be good, but I never see.
Maybe in relation to this, like you said, just made me think of like, because each gradient step is sort of like is each gradient step is public, right? Like we assume that
After you know, make them noisy, yes, you can make them public. But
right,
not
so,
before.
so like is it correct to say that instead of publishing just the final version of the weights after training, I can equally well publish the whole sequence?
Yeah.
Right. So then, could you, for example, look at the first, sorry, like if you're at step N, the optimization, look at say the last 100 steps, and so that gives you some like noisy path weight space. From that, you can maybe estimate correlation. So then the noise that you add in the next step, like moves you not too much in the directions that are harmful.
I know that some works, I mean, they said that we don't need to reveal the intermediate, the output of the intermediate training. For example, from equal 1 to 10, you don't need to reveal anything. And from that onward, you want to reveal. So they try to improve the privacy guarantee there that if you don't reveal something, so you don't need to make it noisy or make it differential private. But I've never seen something. I call it intermediate hidden state. So the intermediate state.
Yeah, there are some like white box where they assume you have access to all the training steps. But still the differential privacy guarantee holds even in that case. But yeah, I don't know. Not sure we've answered your question.
I'm not sure that it was a very clear question.
But there are, I have read a couple of papers where people try and reduce the noise as a post process after that. But yeah, basically all of the methods are trying to sort of say, okay, the noise is there. Can I mitigate it in some ways, either reduce the noise or, as Ali was saying earlier, change the loss function, make it less sensitive to the noise, etc.
Or reducing the dimension of the gradient.
Yeah, it's quite a lot of, especially in images or even the language models, the dimensionality is pretty high. If you can lower that dimensionality, it also reduces the effect of the noise. So it's a thing. But it's interesting, there's a lot of government regulation that are sort of requiring differentially private models, especially around census data or whatever, where there be personal data involved. So it may be something that practitioners have to worry about, fairness and privacy.
Like in 27th of March at the Turing, we are organizing a workshop in privacy and fairness in any model. There is a tension between privacy, differential privacy, and fairness. There is some synergy there, so we can someone